We live in a tiny corner of a vast universe. A place filled with an amazing array of cosmic wonders.
There are blazars, quasars, magnetars, pulsars.
Swirling gas clouds, enormous black holes, the collision of colossal objects.
Yet, from the bounds of our small, lonesome planet, we have set out to explore our universe, searching for answers to some of humanity's biggest questions.
Why are we even here? Or maybe I should say, how are we even here?
We even dare to ask, how did it all begin?
We can see the light from the time when the whole universe was on fire.
And was there anything before the Big Bang?
It wouldn't have been like anything that we can ever experience or imagine.
But if we do find it, then that means we can measure the actual conditions of the moment of creation. That's nuts, right?
The Big Bang, right now. Each of us had a beginning. The moment we entered the universe and took our place on this planet. But our planet had a beginning too, as did our galaxy, the Milky Way, and billions of other galaxies. Trillions of stars and planets that make up our vast cosmos. All of it must have started somewhere, even the universe itself.
Every human civilization has some creation myth.
Why are we even here? Or maybe I should say, how are we even here?
How did the universe begin? These questions, they're huge.
Questions that have remained unanswered for much of human history. Only in the last 70 years have we ventured into space in search of answers, to find the origin of our planet, our galaxy, and ultimately the universe.
Back on Earth, the crew of Apollo 8 has a message that we would like to send to you. In the beginning, God created the heaven and the earth. And the earth was without form and void, and darkness was upon the face of the deep. And God said, "Let there be light." And there was light.
The pace of change, of technological advancement, has gone faster and faster and faster. The 20th century just took things to the next level.
The Apollo missions were our first step beyond our home planet, and in a way, a step backwards in cosmic time. It was during the third moon landing that clues to the origin of not only the moon, but the Earth as well, were discovered. Nearly 100 pounds of rock samples were collected from across the Fra Mauro landing site and returned to Earth. After decades of study, scientists were able to date these rocks and rewind time to a violent event that forged not only our moon, but Earth as we know it. In a quiet corner of the Milky Way, a new star shines out over a plain of debris. Over millions of years, rocks collide and clump together, building a system of planets. Among them, the young Earth, a hellish world. Not yet the planet we know today. One more collision will shape it. A collision on a colossal scale. There is another world born nearby the fledgling Earth, Theia. And the Apollo moon rocks have helped us pinpoint the moment when these two young worlds met. Theia, roughly the size of Mars, collides with Earth, shearing off enough material to eventually form the moon, and marking the final stage of our planet's creation. But understanding Earth's origin is just the first step in our scientific quest to find the origin of the universe.
We can start to understand how everything in our universe evolved and maybe start to answer that question about how did we get here.
Since the time of the Apollo missions, our exploration of the solar system has continued to deepen our knowledge. With each mission, we learn more about how the planets and the sun itself were formed and evolved over billions of years. But the solar system, the domain of the sun, is only a small part of a far larger region of the universe, our galaxy, the Milky Way. The Milky Way is unimaginably vast. So big that it would take us tens of thousands of years to travel to even the nearest stars.
There's this great quote by Arthur C. Clarke that goes, "The only way to find the limits of the possible is to go beyond them into the impossible."
We're all explorers and we're all curious, and astronomy is sort of the ultimate frontier, really.
A frontier that's being constantly pushed by new technology.
We have an amazing suite of space-based observatories at our disposal.
And one of these observatories is shedding light on the origin of planets beyond our solar system, taking us one step closer to the beginning of the entire cosmos. Kepler is a planet hunter. Not able to physically venture to the stars, it stares at thousands of them in a small patch of sky for more than 9 years, revealing something remarkable. Almost every star has at least one planet in orbit, meaning there are even more planets than stars in our home galaxy. And the variety is breathtaking.
On the one hand, some things look remarkably familiar, and then other things that look nothing at all like what we've encountered here close to home.
These planets outside of our solar system, they are zombie worlds, lava worlds, ice worlds, worlds where it rains glass sideways.
And Kepler even finds one planetary system that takes us back towards our galaxy's origin. Kepler 444 is a system home to 5 rocky worlds, 117 light-years from Earth. By analyzing the light from this star, the Kepler Space Telescope has helped us to estimate the system's age, more than twice as old as the Sun. So planets existed in our galaxy long before the Sun and Earth were formed. And the Milky Way must be more than 11 billion years old. The precise age of our galaxy remains a mystery. But luckily, we have a tool to help us understand the beginning of all galaxies: light.
Light is a very powerful tool precisely because it doesn't travel infinitely fast. That means that if it has to come to us from somewhere very far away, it needs some time.
Light travels at 186,000 miles a second, slow on a cosmic scale. It takes just over 8 minutes to reach us from the Sun, and more than 4 years from our next nearest star.
When we look at objects that are 1 million or 1 billion light years away, then we're looking at them as they were 1 million or 1 billion years ago.
Light to an astronomer is like fossils to an archaeologist.
By studying ancient light, we can look back towards the origin of our galaxy and ultimately the beginning of the universe itself. And there is one telescope, more than any other, that can help us step back through cosmic history.
The Hubble Space Telescope is the first great observatory. And I say this with an absolute straight face, totally serious. It is one of the greatest scientific missions in all of human history.
In the early 90s, it's set to become the first major optical telescope in space, capable of seeing further out into our universe than ever before, and therefore further back in time.
I actually got to see the telescope before it was launched into space. I was very lucky. And to think that that same object that I was almost in the same room with would be hoisted into space and would be orbiting our little lonesome planet, I just find that extraordinary.
Go ahead, Charlie. Okay, we have a go for release, and we're going to be a minute late. Okay, Charlie. Houston Discovery. Residuals and ratios look good, and we'd like to go to filter state. We concur, Charlie.
Hubble gathers energy from the Sun using 2 25-foot solar panels to power sensors that analyze star light.
All of this specialized equipment just gives us this immense toolbox to be able to find answers that I don't think people ever really expected we would find.
Orbiting 340 miles above Earth's surface, Hubble has a clear advantage over ground-based telescopes.
The Earth's atmosphere kind of blurs out lots of our images. And so by putting the telescope in space, we get these precise, crystal clear images of our universe.
Hubble has revealed our cosmic neighborhood like we've never seen it before.
I was able to look at those images, and immediately I got a very strong sense that this was exactly what we needed.
Hubble has imaged great nebulae, huge clouds of gas and dust, stars at the moment of their birth.
You can think of them as nurseries for stars. They're the places where you have a lot of baby stars all hanging out together.
You see the Ring Nebula, it just blows your mind away, right? It's just like, you think that someone draw a cartoon into the lens. It's so amazing.
They're these stunning images, and they really give us a sense of how stars form.
But Hubble was built to give us a much larger view of the universe and take us back in time.
Our understanding of the universe is limited by how far out we can see. And that is the size of the universe for us.
It's billions and billions and billions of light years in size. It's huge.
We're not a drop in the bucket. We're not a drop in the ocean. We are a single atom in a drop in trillions upon trillions of oceans.
Oceans filled with countless faraway wonders that Hubble shows us as if they are close up, taking us ever deeper into the cosmos and further back in time. Andromeda, our nearest large galaxy. We see it as it was 2.5 million years ago. And Hubble has seen further still, imaging what looks like a cosmic rose. 2 colliding galaxies. The larger galaxy, UGC 1810, is about 5 times more massive than its companion. We see them as they were 300 million years ago. But to wind back the clock to the origin of all the galaxies, Hubble needs to look farther into space than it ever has before.
One of the temptations when you're an astronomer is to only look at the obvious things. But that's just a tiny fraction of everything in the universe.
Hubble's most surprising discovery came when it looked away from the light.
What we did is we turned Hubble toward a blank part of the sky, and Hubble stared at it.
Peering into the darkness for 4 months, Hubble reveals the blackest patch of space is not quite so empty.
What we ended up finding was galaxies upon galaxies going back billions and billions of years, much further back in time than we would have guessed.
It glimpses primitive and unusual galaxies, unlike anything in our current universe. They are celestial fossils that light the way to the primordial past, until eventually, right on the limit of what it can see, potentially one of the first galaxies to form in the universe. So distant that when we gaze upon it, we are seeing 13.4 billion years into the past.
So this awesome and oddly shaped galaxy is called GNZ11. It's the oldest and furthest galaxy that Hubble can see. It is so old and so far away that by the time the Earth started to form 4.6 billion years ago, the light from it had been traveling for almost 9 billion years. So really this is light from right near the beginning of our universe.
GNZ11 is one of the very first galaxies, forming at a time when the universe itself is still taking shape. Just a few 100 million years after the Big Bang. It's a strange galaxy by today's standards. Tiny in comparison to the Milky Way. But filled with enormous, violent stars.
GNZ11 is this crazy galaxy because it's super, super bright. Like, we don't expect it to exist in the early universe. This huge kind of messy monster. And the stars are very young stars. They've only just formed.
These stars probably aren't the very first to form in the universe, but they're close.
What's most remarkable is that not only can we see this galaxy, we're starting to build up a picture of what it may be like inside.
What is kind of exciting prospect is that you could already have protoplanets, if not planets, forming around those first sets of stars.
Delicate objects struggling in the maelstrom created by these tempestuous stars. These may be some of the first planets in the universe.
Somewhere, there was a first planet that formed in the entire universe. We'll never know about it. We'll never know when it formed or where it formed or what its fate was, but it formed somewhere.
These are strange primordial worlds. But their birth is a key part of the universe's development. The beginning of a relationship between stars and planets. A relationship that will, billions of years later, on one faraway world, lead to life. You and me. But long before even the first stars and galaxies existed, the universe was a very different, very inhospitable place.
And so the story of the very earliest days of the universe are in many ways a story of darkness.
This is a time astronomers call the Cosmic Dark Ages. We can't see galaxies and stars because they have not yet been born. It's a period that optical telescopes like Hubble will simply never be able to explore.
When we look into the cosmic dark ages, we don't see light from any stars at all.
Long before our planet existed, before even the first stars. Just endless gloom. With no starlight to follow, it may seem as if our quest to find the beginning of the universe has reached its end. But perhaps counterintuitively, the younger starlight we can see offers clues to help us understand the origin of the universe. But not just any starlight. The light from one particular type of star can tell us how our universe grew to be the way it is today. These stars are called white dwarfs. They are the fading remains of stars that long ago burned with nuclear fusion.
So once a star like the Sun runs out of material to burn, it will collapse in on itself and expel material, and what's left behind is a white dwarf.
They are dense planet-sized bodies, usually composed of oxygen and carbon, making white dwarfs, in effect, stellar diamonds.
So these white dwarfs, these stellar corpses, are incredibly exotic objects.
A teaspoon of this material would weigh more than 5 tons.
It's one of the densest objects in the universe. It's just this very small, very hot object that's about the size of the Earth with about the mass of the Sun.
How is it that these strange stars can tell us anything about a time before stars existed, and even give us clues about the moment the universe began? White dwarfs are critically balanced, resisting the relentless inward pull of gravity, but only barely. They're teetering on the edge of destruction. If their mass increases above a critical limit, then gravity takes over. And in 2018, Hubble sees what happens next. The telescope focuses on a galaxy far, far away. NGC 2525. Hunting for a distant white dwarf at the end of its extraordinary life. For millions of years, the white dwarf remains hidden, locked in an orbit around a much bigger star, a red giant. As they circle each other, the white dwarf's gravity pulls in gas and plasma from the red giant. The mass of the white dwarf increases. Until it approaches a critical limit, known as the Chandrasekhar mass. and surpasses it. Triggering a colossal thermonuclear reaction. The white dwarf detonates in what scientists call a Type 1a supernova.
This was an immensely energetic event in the universe with the brightness of 5 billion of our suns. It was so luminous that Hubble could take a time-lapse movie of it as it evolved.
It's the brightness of this event that allowed it to be seen by Hubble. And why catching a Type 1a supernova in the act is so exciting for scientists. This bright light has quite a story to tell.
Everything that's happened to that light on the way from its source to us, everything it's encountered, and including time, has affected what we actually see.
The light from Type 1a supernovae give us a tantalizing clue to how our universe evolved. And it's by charting the evolution of the universe that we can build a roadmap back to its beginning.
So Type 1a supernovae, it's like the universe's free gift to us. Because they all explode in the same way, they reach pretty much the same brightness. So if you see one dimmer than the other, it means it's further away. And that allows us to measure distance to the galaxy that's hosting this supernovae explosion.
We have seen Type 1a supernovae across the entire universe. We can measure the distance to their home galaxies. And that can tell us how the universe is changing over time.
So when we look at distant supernovae, we see something really interesting. Their light's not just dimmer, it's redder. And the further away they are, the redder their light is. But as the light travels from this distant galaxy to us, space itself is stretching. And so the light gets stretched along the way. It gets redder. And this is called redshift.
We see the effect of redshift in the light from every distant galaxy. And that means space is stretching everywhere.
And that means something truly amazing. It means our universe is expanding.
By studying how galaxies themselves are red-shifted, we have known for nearly a century that the universe is expanding. But by using Type 1a supernovae to study it in detail, we can accurately tell how fast our universe is growing. And what scientists find is something completely unexpected.
Astronomers working with the Hubble Space Telescope started to realize that the universe is not just expanding, but it's actually expanding at an ever-increasing rate.
It's that accelerated or speeding up stretching that really did catch our community by surprise.
We know the universe is expanding. And thanks to Hubble, we have evidence that this expansion is accelerating over time.
So if you know the universe is expanding, you can just do a thought experiment and turn time backward and know that the universe was smaller in the past.
We can wind back the clock through thousands of billions of yesterdays. Back to a time before our Earth and Sun. To a time before the first galaxies. And finally, we can cross the cosmic dark ages to pinpoint the moment the universe began. A moment we know happened 13.8 billion years ago. The Big Bang. The moment when our universe burst into existence. Yet, it wasn't anything like an explosion.
This is the initial state of the universe, which was very hot and very, very dense.
Everything, the whole universe, was held together in a very tiny region of space.
So everywhere in the universe is almost like being inside of a star.
All the matter that has ever been produced came from that moment in time.
These conditions are unbelievably extreme, and they no longer exist in today's universe.
It almost seems miraculous, if not ridiculous, that we could study the origin of the universe, right? People say to me all the time, how could you know? No one was there.
For decades, the Big Bang has been science's best estimation of how the universe began. And in 2009, a mission is launched to try to get a better understanding of this time in our universe. The European Space Agency's Planck telescope is designed to look for the remains of the Big Bang. Not starlight this time, but a different type of light. The afterglow of the Big Bang. The most ancient light in the universe.
If we do find it, then that means we can measure the actual conditions of the moment of creation. That's nuts, right?
Planck will measure this ancient light with more precision than ever before.
Sept, six, 5, 4, 3, 2, 1, top.
The moment of the launch is where everything is at risk. And not just the launch, there's a whole bunch of stages.
There was palpable excitement because we knew that this was an amazing shot we had at understanding our universe better.
It's a 2-month journey for Planck to reach its destination, far beyond the orbit of our moon. Once in place, Planck meticulously scans the entire cosmos over and over again.
anything that's hot tends to send out light. So if the early universe was really dense and hot, there should be a load of light left over from that time.
Using its 5-foot mirror and 2 detector arrays to capture light in the form of microwaves, Planck builds a map of the furthest reaches of the universe. Looking back to a time long before galaxies and stars. After 4 years of ceaseless scanning, scientists are finally able to glimpse a snapshot of the aftermath of the Big Bang in spectacular detail.
So this image that I'm looking at here is one of the most exciting images in astronomy and cosmology. And it's an image of the cosmic microwave background radiation. So basically the Big Bang happened, and this is the first light that we see that came from that event that basically birthed our universe.
Thanks to Planck, scientists now have a detailed image of the entire universe in its infancy.
The best analogy of looking at the first light of the instrument, I think, is like seeing your child being born.
We can see the light from the time when the whole universe was on fire, when the universe was not empty space, but a roiling, churning plasma.
We can look back to within 380,000 years after the Big Bang. Before that, we can't see any light because it was all absorbed by the universe itself.
It may not be an image of the Big Bang itself, but the cosmic microwave background is powerful evidence that it did happen.
I couldn't wipe the smile from my face for about a week.
Planck gives us details of the earliest moments of the universe. And at first glance, all it sees is an almost featureless glow.
So no galaxies, no stars, just this glowing ball of plasma. And the radiation reflects that actually, because when we first looked at it, this radiation was incredibly smooth.
But Planck's highly sensitive detectors can pick up even the slightest variations. Variations we see as different shades of blue, red, and yellow in this iconic false color image.
Before, all we could see is a uniform glow. Now we can actually see small patches on the sky, differences in temperature, which are really incredibly tiny.
The variations are less than 100,000th of a degree. But they suggest that the primordial fireball was not perfectly uniform, and these variations must have come from somewhere, pointing to a profound truth. The Big Bang was not actually the beginning. The earliest moments of our universe are very strange. There is no matter. All that exists is space-time and energy. An ocean of energy, almost uniform, but not quite.
It wouldn't have been like anything that we can ever experience or imagine. It was a field of energy that had tiny, tiny quantum fluctuations popping in and out of existence.
These fluctuations, ripples in the ocean of energy, hold the key to our universe today. They are the origin of everything.
If these fluctuations didn't exist, there wouldn't be a single star, there wouldn't be a single bit of cosmic dust or anything like that, and we certainly wouldn't be here.
Imagine a speck in that ocean of energy. This speck is about to grow so big, it can accommodate every star and galaxy in our universe. It just needs to grow fast.
That energy would drive a remarkably rapid stretching of space, an exponentially rapid stretching. So space would not just get bigger, it would get bigger faster at a mind-boggling rate.
In the briefest of instants, for less than a billionth of a second, the speck expanded much faster than the speed of light. A moment in time we call inflation.
So in this infinitesimally small time, our universe went from something that's smaller than an atom to the size of a basketball.
That's an amazing amount of stretching in a very brief window.
We don't know why it started, and we don't know why it ended. When that rapid expansion slowed down, something happened that dumped a bunch of energy into the universe, created this fireball state.
Inflation creates the Big Bang. But it was not, as we commonly imagine, some kind of explosion. It was largely a transformation. A transformation of energy into matter. And the rapid inflation left its mark. The tiny fluctuations in the rippling ocean of energy became imprinted into our universe.
Those little quantum fluctuations, they would have gotten stretched as the universe itself stretched so rapidly, so dramatically. So a little wave of unevenness that starts out during inflation would get stretched to astrophysical scales.
The fluctuations that existed before the Big Bang go on to create everything we see in the sky today. Gravity takes hold of the tiny variations that now crisscross the young universe, creating great clumps of matter, but also great voids. Spinning a web-like pattern that spans the universe. The densest regions collapse to form the first stars. And the first galaxies. After 9 billion years of cosmic evolution, a new star is forming in the Milky Way, our sun. Eight planets emerge, including our planet, Earth. Here is a place where the elements combine. Hydrogen, formed in the Big Bang. Carbon, oxygen, and others, forged in the hearts of stars to create life. Us.
We are a speck of dust on a speck of dust. We're totally unimportant to the universe in any possible way you can think of. And yet, we can see the beginning of the universe.
I think it's very humbling that us, as humans, we have come to understand so much.
The universe has somehow opened itself for us to study. And maybe that's our only purpose. I mean, maybe the universe created us so that we would understand it.
We are going to be but a sentence in the book of the universe. And so I think it's incumbent upon us to write the best possible sentence that we can. I cannot wait for what is to come.